Okay, let's start the second lecture of this course, which is AP 1027, Maxwell Equations and Electromagnetic Waves. At the bottom of the screen again, you have my email and Skype info for office hours. So the agenda for today's lecture is going to be Algebra and Calculus of Vectors and Tensors. This is what we're going to do. We're going to do a short review of our lecture 1. We didn't really do much, but still I think it's important we review a little bit of the notation and convention which I introduced in the last class. And then I will define vectors, scalars, and tensors using the transformation law under rotation of coordinate axis. I will tell you what I mean exactly by this. And then we will define vector fields, scalar fields, and general tensor fields. Okay. So these are different from vector, scalars, and tensor. Field, the word field, the moment we add the word field, they become functions of space. And then once we have vector functions of space, we will start defining differentiation of these objects. So we will consider three prominent first order derivative objects, which are gradient, divergence, and curl. And then there's one single important second order derivative object, which is the Laplacian. And then I will talk about integration of scalar fields, vector fields, and general tensor fields over either two-dimensional surfaces or over volumes, so volume integrals and surface integrals. And of course there is a line integral, which is integration over a line over a clear one-dimensional curve. And we will learn about two important theorems which should be thought of as the multivariable analogues of the single variable theorem, fundamental theorem of calculus. So there are analogues of that in multivariable calculus, which are known as Gauss theorem or Stokes theorem. We will learn them because this is how we will actually do the integrals. Okay, so without further ado, let me just also give you the references for this lecture. That is, I'll mainly follow Griffith's chapter 1. This is a nice chapter on vector calculus in general. There's a nice book by Mary L. Bose, which is also very popular at the freshman and sophomore level, Mathematical Method for Physicists and Engineers. This chapter 6 is on vector calculus. You can take a look if you find the presentation of the material in the lecture to be too brief or too abbreviated. And then for problems, I would suggest Marie R. Spiegel's book, Schwamm's Outline of Vector Analysis. As most of you know, analysis is just another word for calculus. So vector calculus, you have a lot of different problems. You can practice them from Spiegel's book. It's a nice book in the sense that it takes you through the subject by means of solving problems. And then the fourth one, I actually haven't read it, to be honest. This was suggested by Griffiths in his book. And he says that this is a very nice text, so it must be, I kind of trust everything what he says, because it, more or less, it matches with my intuition. So maybe this is also a good book to look at stuff, Divergence, Curl, and all that in formal text. But yeah, everything what I'm saying is already there in Griffiths. You don't need to look around too much. Okay, so let's start with the recap of our last chapter, our last section. So we introduce vectors as quantities which have magnitude and direction, and usually represented by a directed line segment, which behaves like a position vector under vector addition, under multiplication by a scalar, and transforms like the position vector as well under rotations of coordinate axis. Okay, so this is in boldface because this is going to be our main criteria to distinguish vectors from anything else. Okay, it's something which should transform just like a position vector under rotations of coordinate axis. So position vector, what is position vector? We also reviewed a little bit. We had set up a Cartesian coordinate system, and then the position vector of an object is a three-component object or a triplet, giving the location from origin of the coordinate system, location of the object from the given origin of a coordinate system. You can think of it as a row vector, xyz, or as a column xyz, which is what I'm going to follow in this course. Any vector by default will be a column vector. and then the row vector will be given by the transpose of the vector. Okay. So because we are moving from position vector to general vectors, I will introduce a slight change in notation. Now I'm talking about a general vector. I won't use x, which is usually for position vector, or r in the book. Instead of x or r, I will use initial alphabet letters a, b, and c, for example, to denote the components, denote a vector which is not a position vector. Okay, a instead of x, y, z. And of course, the indices, components will be given by Latin indices, and they'll be given by middle alphabet indices, K, L, M, and so on. Okay. So a sub k is the kth component of the vector a. The full vector is of course denoted in boldface, or when you are writing, you should write with an arrowhead, or at least a bar. If not an arrowhead, just put a bar. But if you leave in your answer script, if I find you denoting vectors by without any bar or arrowhead, then you stand to lose credits for that. We also introduced the rule for addition of two vectors. This is very simply done when you write down the vector in components, in triplets, and the vector sum is defined to be a new vector whose components is just the algebraic sum of the respective components. So a plus b is the new vector whose components is the sum of the x component of a and b, y component of the new vector is the sum of y components of a and b, and so for the third component as well. And then the rule for multiplication by a number of scalar. So when you multiply a vector by a scalar, the rule is that you multiply each component. The new vector, it has components whose components are multiplied by the same vector, same number, lambda a1, lambda a2, lambda a3. And this I already explained before. Once we choose a vector to be a column, then to denote the row vector, we will use the transpose, a of a transpose, which is a1, a2, a3 in the row vector. Okay, we also introduced some more notation in which we wrote the vector in terms of a preferred basis, which are denoted with a set of three vectors. Because this is a three-dimensional vector, we will need a basis, basis comprising of three elements, three vectors, special vectors, e hat 1, e hat 2, and e hat 3, which are given by this. So any vector can be written in this form. The first component times the special vector, which is basis element 1. Second component times basis element 2, and third component multiplied to special vector, which is the basis element 3. So these three elements form a basis, e1 hat, e2 hat, and e3 hat. And then in terms of these, we can write any vector can be written in this way. It's some basis element times the component, and then you sum over the basis elements, so you can replace 1, 2, and 3 by ak, and then you sum over k going from 1 to 3. Now this sum is unnecessary. As I said, we are following Einstein's summation convention. Because k is a repeated index, we can forget about the sum, so we will just write this thing without the sum, without the summation symbol. So a vector is written by its component times the basis element, and because it's repeated, it's implied the sum over all basis elements. We also introduced the dot product or scalar product or inner product of two vectors. So a and b, the dot product is defined to be a transpose times b in terms of matrices or row vectors. So this is a row vector and this is a column vector. So it will give you a number, or 1 by 1 matrix or a number. So this is number is equal to a1 b1 plus a2 b2 plus a3 b3. From this form, it is clear that if you switch a and b, the place of a and b, this remains the same thing. So the scalar dot product is symmetric between a and b. So I could have well written it as well, a b dot a instead of a dot b as well, and it makes no difference. Now this can be written in this index form as ALBL, with L being summed over 1, 2, and 3. The first term will give you this on this term, the second term in the sum will give you this, and the third term will give you that. So And then again we use Einstein convention, in which we get rid of the sum because L is already repeated, it's a repeated index, so the sum is automatically implied, AL BL. Okay, now we will write it in a slightly different way as well in future for future convenience. So BL can be thought of as BM times delta LM, but delta is the Kronecker delta, right? We introduced in the last class Kronecker delta is 0 whenever its components take different values. L and M are different, the indices take different values. Then this is 0, and this is non-zero and equal to 1 when the indices have same value. So L is equal to M, only then it will be plus 1. Now M is the dummy variable here, so M gets summed over everything. In particular, this will be non-zero when M is equal to L. Other values of M will just give you 0 because the Kronecker delta is 0. So the solution of this is that just replace the M by L. So if you replace the M by L, so this becomes BL, and delta LL is of course 1. So BL is equal to BL, you get back. So this is equal to same as BL. So if this is so, then in AL BL, if I replace the BL by BM delta LM, I'm sorry, this should be in the subscript, not like this. I'm sorry about this. So the AL BM delta subscript LM. Okay, so this is another fancy way of writing the dot product. Then we introduce the norm of a vector, which is given by vector A within this double bar, and this is defined to be square root of the self dot product. In index notation, you have AK square root of that. We also introduce the vector product of the cross product of two vectors, it is very clear why this is called a cross product, because there's a cross in between and the multiplication is a cross instead of dot. And it's called a vector product because the resulting quantity is a vector. Because the resulting quantity is a vector, it can be expanded in a basis, EK hat. So EK, then this is the component. So the kth component of the vector A cross B, cross product, along the kth component is given by this formula, epsilon ijk, ai bj. So important thing to note is that the dummy index is same on both, the free index is same on both sides. This is one rule to follow when you're working with indexed expressions. Whenever you have an equation, you should check that the both sides have the same free indices. The number of dummy indices doesn't have to match, and the reason is that dummy indices get summed over everything. So at the end of when you perform the sum, after you have performed the sum, these indices do not appear anymore because they have been already summed over. But free index is still there because it can take values whatever it wants, doesn't have to be necessarily summed over everything. So to check if some indexed vector equation is correct or not, you should check the number of free indices on both sides. In this case, k is the free index, I and j are dummy indices, so they go away, so they don't have any existence left over after the sum is performed. So this is fine. So epsilon ijk, as I said in the last lecture, is the completely antisymmetric symbol, or Levi-Civita symbol. So it is antisymmetric under swap of any two of these three indices. You take any two of these and you swap them, you pick up a minus sign. And in particular, it is for epsilon 1, 2, 3, when I equal to 1, j equal to 2, and k equal to 3, Levi-Civita takes the value plus 1. The other values can be figured out by the fact that it is completely antisymmetric. For example, any cyclic permutation of 1, 2, and 3 will be obtained by even number of swaps. So because you're doing even number of swaps, it will pick up even number of signs, which means it will stay plus 1. On the other hand, every anticyclic permutation of 1, 2, and 3 will give you a minus 1. For example, epsilon 1, 2, 3 and epsilon 1, 3, 2. 3, 2 is obtained from 1, 2, 3 by swapping 3 and 2. Swapping the 2 and 3. And it's a single swap, so that's why from plus 1 you will get minus 1. Anything which is repeated, because of antisymmetry, that will vanish because it will be minus of itself. Anything which is minus of itself is 0. So this is how we define, and we also checked that indeed if this formula gives you the correct result if I put, for example, k equal to 1. That is, if I'm looking for the first component, x component of a cross b. 1 is the x component, and so k is 1. If k is 1, I and j, so we have ij1 ai bj. If k is 1, I and j can be 2 and 3 or 3 and 2. When it's 2 and 3, 2, 3, 1, you have I equal to 2 and b equal to 3. Epsilon 2, 3, 1, epsilon 2, 3 is plus 1, you get this. And when k is 1, I can be 3 and j can be 2 as well. But 3, 2, 1 is minus 1, so minus a3b2. So indeed, it reproduces what you had learned in high school, the cross product, which is given by some kind of matrix form, ugly matrix, big matrix form. Instead, you have a one-line way of writing, compact way of writing in terms of indices, using the Levi-Civita. Now, vector transformation rule, this is what I wanted to introduce. That should mimic, as I said, the transformation rule of components of the position vector. So the position vector is x, and its components x1, x2, x3. Now, when I rotate our coordinate axis, and then in the new coordinate axis, the same vector, position vector, has different components. The new and the old components are related by this kind of a transformation. It's a linear transformation, linear homogeneous transformation. So in that case, they can be written as the matrix version, and this is the compact form of this. So matrix O multiplied by matrix X gives you matrix X prime. In fact, this is not just a matrix, it's a column matrix or a column vector. So this is how, this is the compact way of writing how the components of a vector change under rotation of the coordinate axis, Cartesian coordinate axis. Now this equation in boldface can also be written in terms of indexed object. For example, I can take the I component of both sides, so x prime I, and OX, this is the matrix product. We know how to take the matrix product. The column index of O must meet the row index of X, which is something like this, right? So OIJ xj equal to xi. This is an important formula because we will need it. That's why I demarcated this in red. And the reason this rotation, as I said, is an orthogonal matrix is to preserve lengths or norms of vector. When you rotate the coordinate axis, the length of a vector doesn't change, which means the rotation matrix must be an orthogonal matrix. Okay, so O transpose O should be identity. This we checked last lecture. And then we also saw that when you write this equation in indexed notation, you get this form. So these are matrices. Instead, now these are just regular numbers or components of matrices or elements of matrices. OIJ, OIK equals delta JK. Again, if you look at both sides, identity matrix, so that we are looking at the JKth element of this equation, matrix equation. JKth element of this matrix equation. Now, if we look carefully, the number of free indices on both sides match. So JK, JK. On the other hand, I is the first index of these O's are I's, which is summed over. It's a dummy index, so that's why it doesn't retain its existence after the sum is performed, and only J and K remain. So that's why this is a correct expression. And we also check the fact that orthogonal matrices are rotation matrices are orthogonal by looking at the special case when we rotated the xy plane around the z-axis by theta, by an angle theta. The matrix corresponding to that was actually this. In fact, we looked at 2 by 2 sector, but then you can embed a two-dimensional plane inside a three-dimensional space by thinking of that two-dimensional plane at the z equal to 0 plane as a z equal to 0 plane. In that case, the coordinate doesn't transform at all, so that's why 0, 0, 1 is the third column and 0, 0, 1 is also the third row. And then we explicitly check that indeed, and this is O transpose equal to O inverse, or it's an orthogonal matrix. Now let's look at the general case. When I have, instead of x, I have a general vector A. Doesn't have to be a position vector. The way you define this is that a vector A is an object whose components transform under rotation of the coordinate axis as this. All I've done here is that taking the rule of transformation for the position vector and replace the x by a general vector. So both these equations, this is what I've done. Instead of x I have a. Instead of x I have a. So this is the definition of a general vector. A general vector is something which will respect the transformation rule under coordinate rotation, which is the same rule as respected by the position vector. Okay, so again, same thing. If you look at both sides, the free indices match. Number of free indices is one index on both sides, and then j is summed over, so it doesn't retain its existence after the sum is performed. One can also introduce objects which are known as scalars, and they are defined to be objects which remain unchanged under rotation. So phi prime is equal to phi. Okay, phi is a scalar, and in the rotated frame, which is when we put prime, we are distinguishing the primed frame components, the rotated frame components by a prime. So this, whenever you see a prime, that means I'm talking about the component of that object in rotated frame. Okay, so in the rotated frame, the component there's only one component, and that remains unchanged. So this is how we define a scalar. An example of scalar quantities are rife in physics. Most of you know from high school: mass, time, norm of a vector. As you know, the size of a vector doesn't change if you rotate the coordinate axis, and you can know that you explicitly know this for the position vector. You can also check that the dot product of two vectors is also a scalar quantity. And remember, the dot product, when we write in index notation, is ALBL, right? A dot B in index notation is ALBL. L is summed over, it's a domain index. Now we can check that this is indeed a scalar. So let's check this. So on the left hand side, what we have, phi prime, as I said, phi, in the primed coordinate system, the rotated vector dot product of two vectors is a prime dot b prime. Now the way we define the dot product is that we have to take a transpose of the first one, and then b, you leave it as a column vector. So this is a prime dot b prime is a prime transpose multiplied with b prime. But these are vectors, so under rotation they will transform like this. So we replace the a prime by OA. So a prime we replace by OA, transpose of that, whole transpose. And then b prime we replace by OB. Now we perform this transpose. Whenever we take transpose of a product of matrices, we know that the order gets reversed. So OA whole transpose is equal to A transpose O transpose, and then OB remains as it is. But O being an orthogonal matrix, O transpose O is identity. So you have A transpose B. This is identity. So A transpose identity B is just A transpose B. But A transpose B is just A dot B, right? Which is the scalar phi. So A dot B we had defined to be phi. So we get phi prime equal to phi. And this is how we had defined the scalar. So scalar did not change under rotation, which is an orthogonal transformation. Similarly, we can introduce tensors, which are more general objects than vectors and scalars. Scalars have no free indices, no index, as you can see, only a domain index L, no free indices, and vectors have a single free index. You can define objects with multiple free indices. For example, there are p of them, I1, I2, so on to IP. So there are p free indices. That defines something which is known as a rank P tensor. So I'll give an example, because for the transformation rule for a general rank P tensor is a bit cumbersome, and it is not really insightful. It is more insightful to consider subcases, like for example rank 2 tensor, which has two indices, I1 and I2, or in this case I've denoted I and J. So it's a two index object. Under rotation, coordinate axis rotation, the components of that vector, of rank 2 tensor, transform like this. Now, if you note at the transformation rule for the vector, you will see for every free index there is an O. So this rule we also have for the tensor. There are two free indices. For each free index, we have a factor of the orthogonal transformation, OIJ. So for I and j, we have OIL and OJM. For each free index, you have to put a factor of the orthogonal transformation. And whatever are the left indices, you contract over with multiplying with the TLM. So L and M are dummy indices, they get. So you must have, I uttered this phrase of contraction. So what do I mean by that? What do I mean is, by contraction means whenever you have dummy indices, after you perform the sum, that index gets lost, right? So that is what is called a contraction. We get the number of indices will become shortened, right? AL, BL, after you sum this, you don't have, the resulting object doesn't have that index. So that's why it's called a contraction or shortening of indices. Here also J is contracted, so the final expression doesn't have J. The number of indices from 3 to, we had a reduction, a shortening to 1, that's why it's called a contraction. Okay. So this is the definition of rank 2 tensor, which has 2 free indices. We have 2 factors of the transformation matrix times TLM. Now, there are examples in physics where you have this as well. One prominent example of rank 2 tensor is the outer product of 2 vectors, AI, B, J. It is pretty clear. Now, unlike the dot product, which is symmetric, and the cross product, which is antisymmetric, AIBJ is not symmetric under the swap of A and B, and neither is it antisymmetric under the swap of A and B. So it is just a general case, AIBJ, and there are 2 free indices. That's why this is a rank 2 tensor. And you can easily check that it obeys this transformation law as well. Another quantity which is the rank 2 tensor is the Kronecker delta ij. This is a bit of a special case. We will just see in a moment that this is a very special rank 2 tensor, which will end up being an invariant quantity. And then there is also moment of inertia, which you have hopefully have learned in rigid body mechanics in the first course on mechanics. So moment of inertia tensor, I'm sorry, this formula got a bit too below the view. So what I have is big I, the letter big I denotes the moment of inertia, and then little I and little j are the indices. You cannot see, you can only see the dots of I and j here, but this is big I subscript little I and little j equals m times delta ij xl or something xk minus xi xj. So it's an outer product of xi and xj, and it has a Kronecker delta. Each of them is rank 2 tensor, so sum of or difference of 2 rank 2 tensors is also a rank 2 tensor multiplied by a scalar. So if you multiply any tensor by a scalar, its rank doesn't change, it remains the same rank tensor. Okay, so moment of inertia is the first, I think the first non-trivial rank 2 tensor you learn in physics and mechanics. So as I was saying, that Kronecker delta is a bit special because it belongs to a special category of tensor which are called invariant tensors. What do I mean by invariant tensor? It might sound oxymoronic, because tensors are supposed to obey some kind of transformation law, but I'm saying that they're invariant, so they don't transform. Invariant transforms the components tensors whose components remain unchanged under rotation. This sounds a bit paradoxical. This cannot be true. They're supposed to change like this. How can they remain unchanged? But rest assured, this happens. And one prominent example is the Kronecker delta ij. You can show that if you rotate your coordinate axis in the new coordinate system, the components remained unchanged. Let's see how this happens as a short proof. So this is a rank 2 tensor. So this will, first of all, delta will obey the transformation rule for a rank 2 tensor. For a rank 2 tensor, for each free index, we're supposed to put a factor of the orthogonal transformation on the right, and then for every other every other index, we're supposed to contract with the same tensor. So it's basically what I've done is taken this formula equation for the transformation rule of rank 2 tensor, and I've replaced the t's by the deltas. Okay. Now, as I've done before, this M is the dummy index. M is getting summed over, and this is the Kronecker delta. So this sum will only not vanish when M is equal to L. So M must be replaced by L. So I've replaced Jm by Jl, and in that case M and L are same and equal to 1. So this is equal to OIL is untouched, but OJM becomes OJM delta LM becomes OJL for the reason I already told just now. Now this, I want to write this as a matrix product. So if you want to write this as a matrix product, the column index should match the row index of the next guy, but it doesn't really. Here both column indices are L. So to make L into a row index of the second guy, I have to take a transpose. If I take a transpose, then JL will become LJ, right? Because the rows and columns get swapped. So I have OIL, O transpose of L sub LJ. Now this is starting to look like a matrix product. So I can take a matrix product, O transpose, and the resulting row and column is I and J. So O transpose I and J. But O being an orthogonal matrix, O transpose is equal to identity. Just as O transpose O is equal to identity, O transpose is also identity. And in that case, so this is identity, and ij component of identity is just delta ij. Thus, what we have here is that delta prime ij, which is the ijth component in the primed or rotated frame, is equal to same. This is nice because this means that all frames, it doesn't have to be which frame, in all frames delta 1 1 in any frame is always equal to 1. Delta 2 2 is always equal to 2. Delta 3 3, we don't have to worry that okay, this was 1 1 1 in one frame, but maybe in a rotated frame it will look like 2 3 4 or something. No, it doesn't happen like that. It is an invariant tensor, so even after rotating, even doing that orthogonal transformation, you will find that the respective components remain 1 when I and j are the same, and equal to 0 when I and j are different. Okay. The second prominent example of an invariant Cartesian tensor is the Levi-Civita tensor. For that, to see why that is so, we have to learn a little bit about the determinant. Most of you are familiar with the determinant of a matrix M. So M here is a 3 by 3 matrix. So and this absolute value kind of sign means the determinant. So when I'm talking about a matrix, whenever you see this bar enclosing a 3 by 3 matrix, you should know that I'm talking about a determinant of that matrix. Okay. Other ways of denoting the determinant you find in books is the letter det or something. I'm not going to use that because it's a bit cumbersome. I'm going to use this single bar to denote the determinant of a matrix M, and this is equal to epsilon L and M times M1L, that is the first row element, Lth element of the first row, M2M, that is the mth element of the second row, and M3N, that is the nth element of the third row, right? You can check that this formula is indeed true. You can expand L and N are all dummy variables, so you have to take all values, and you will indeed see when you write down, this will give you the usual formula for the determinant, right? That you can check on your own, or I will maybe put a supplementary note where I show this is indeed true happening. So this is the definition of a determinant. You don't use the matrix form. That is ugly thing to write, so you have a nice compact way of writing the determinant in terms of the Levi-Civita. Now a slightly more generalized version of this formula is the next formula in the next line. Instead of 1, 2 and 3, I have replaced them by arbitrary free indices I, J and K, I, J, K, and then since free indices must match on both sides, I have put an epsilon I, J, K. You can check that this is also true. In particular, when I take I, J, K to be 1, 2, 3, it reduces to the first line. Okay, so this is just a generalized version of the first line, and the first line is the definition of the determinant. Okay, this might not be very familiar to you, but rest assured, this is a very nice way of writing the determinant and something which you ought to know, especially in vector calculus. Now, this definition of the determinant will help us in demonstrating that the Levi-Civita is an invariant Cartesian tensor. How so? Let's see how so. So this is a rank 3 tensor because it has 3 indices. So for every free index, as you know, the transformation rule says that the new component ijk in the prime frame, for every free index I have to put a O, a factor of the transformation matrix O, so I, OI, J, OJM, and then for the kth index I have OKN, and then number of free indices are same, so the dummy indices needs to be contracted, LMN should be contracted with epsilon ln m, right? So this is the transformation rule for a rank 3 tensor. But notice that this is exactly the right hand side of this formula for the definition of a determinant, except in case of instead of m I have O's. So if this is equal to this must be equal to determinant of O times ijk using this definition of the determinant, right? So this is same as that. And what is the determinant of an orthogonal transformation? Let's check. For rotation, I'm sorry. So this is a rotation. Let's check what is the determinant. Well, the determinant will turn out to be cos squared theta plus sin squared theta times 1, that is 1. This will turn out in generally to be 2 for rotation matrices. The determinant of the rotation matrix is always equal to 1. So you get epsilon prime ijk. So ijk component in the prime frame is same as the ijk component in the unprimed frame. So this is again showing that Levi-Civita is an invariant Cartesian tensor. So there is a small caveat there. What I've actually defined here, the way I have defined the vector, that objects which transform like the position vector under rotation of coordinate axis. This is actually not a general vector. This is what is what some people call is a polar vector. Okay, something which is called an axial vector. Now we can define polar vectors for a different set of orthogonal transformations. So let me just go back to the definition of an orthogonal transformation. Yeah, so this here. As I said, rotation matrices are orthogonal transformations, but the reverse is not true. The converse is not true. Not all orthogonal transformations are rotations. For example, if you take a determinant of this equation, O transpose O equals 1. If you take determinant of the left hand side, this becomes determinant O squared equal to 1. Because the identity matrix, the determinant of identity is 1. So we have determinant of O squared equals 1. That means determinant of O is plus or minus 1. Now the plus 1 case corresponds to rotations, and the minus 1 case corresponds to not a rotation, but a reflection or change of handedness of the frame from left-handed coordinate system to right-handed coordinate system. So physically, orthogonal transformations are of two kinds. One kind of transformation is a rotation, and the other kind is change of handedness of the coordinate system from left-handed coordinate system to right-handed coordinate systems. Now you can demand that I define vectors to be to transform like the position vector under both rotations and change of handedness of the coordinate system. Then those vectors are known as polar vectors. Or you can define vectors as those which transform like the position vector only under coordinate rotation. These are called axial vectors. Okay, it turns out that so polar vectors satisfy a most stringent criteria because they must transform like the position vector under both rotations and coordinate change of handedness of the coordinate system from left-handed to right-handed. So there's a much more stringent criteria. If you follow that criteria, then epsilon is not an invariant tensor. Kronecker delta is a polar tensor because no matter what orthogonal transformation this is, whether it's reflection or that is change of handedness of the frame or its rotation, it's always going to give you identity. So it's the same. But Levi-Civita for reflection, this is equal to minus 1. So epsilon prime is not equal to epsilon but minus of epsilon. So it got changed. Its component got changed. So in right-handed coordinate system, if you take to be plus, in the left-handed coordinate system, the same, you have to take the component to be minus. So in this sense, this is an axial object or an axial tensor because it obeys the transformation invariance under coordinate rotation, but not under reflections. In general, the cross product of two vectors, the resulting vector, is an axial vector. It's not a polar vector. So again, if you look at the behavior of this under reflection of coordinate systems, that is the change of handedness from left-handed to right-handed, it does not behave like a position vector. So that's why it only behaves like a position vector under rotation. So that's why this is an axial vector and not a polar vector. So you can check, the point of this is that you can check that the cross product is a vector, or more precisely an axial vector, by looking the behavior of this quantity, of this indexed object under rotations. And you'll see indeed it transforms following this rule, right? So this is a vector because it has a single free index k, I and j are summed over. So it will transform like this. You should do a homework in which you should check this, okay, and convince yourself. Now for tensor fields, we can define a tensor fields, I haven't defined tensor fields yet. Tensor fields are when you have at each point in space a scalar field, then you call that a scalar field. I'm sorry, when at each location in space you have a scalar sitting there, then you have a scalar field, right? At each location in space there is a vector sitting there, small arrow you can imagine. At each point in space, then you have what is called a vector field. And you can generalize this thing. At each location, if there is a tensor, in this case we have a rank 2 tensor sitting there, then you have a rank 2 tensor field, okay? So as you change the location, the tensor or the vector or the scalar will change. So here are some examples. For scalar fields, we can look at the charge density field. So if you have some charges distributed in space, at each point in space, the density, local density, is given by the charge density function. And then electric field is an example of a vector field, because at each location in space, you have an electric field, a small arrow there. And then for the rank 2 tensor field, we can define, if we have a dielectric, we will see that we can define a susceptibility tensor, chi of ij, at each position in the dielectric. Of course, if it's a uniform dielectric, then at all points the value of this is the same. So it's a constant function. Now when we have such kind of objects, we will be curious about how these are changing as I change the location. So then we need the notion of a derivative. However, remember that boldface x means it's a triplet, so and all these quantities are multivariable functions of multiple variables. In particular, they are multiple component objects as well. So multi-component objects of multiple variables, right? So for multiple variables, we know we need the notion of a partial derivative in general. So there are many derivatives possible, infinite number of ways you can take a derivative of a quantity, because you can take study the rate of change in any arbitrary directions, and you can have infinite number of directions in three-dimensional space. So you can imagine infinite number of lines, so you can take derivatives along any different direction. So it makes sense to define something which is known as gradient of a scalar, okay? So what do I mean by that? Let's start with the difference in the value of the scalar when I go from location x to x plus dx. d of x is a small quantity. So if I change the location of my object, of the location from x to x plus dx, because this is a scalar field, at x plus dx there is a new scalar sitting there. So I want to find out what is the difference between the value of the scalar in these two different neighboring location. Now this guy I can expand using multivariable Taylor expansion with to linear order because this is very small. So linear order is going to be important in the limit dx going to 0. So linear order Taylor expansion we will keep. So the leading order will get cancelled with phi x, and then we will have the linear order result, which is this. So look at how this quantity shapes up. For You can think of this as a multivariable Taylor expansion in linear order. So derivative times the difference, derivative, partial derivative, second order, second component times this, and third times this, right? Third change in the third coordinate times the partial derivative in the third component. So this is the linear term in the Taylor expansion of this quantity. Now this can be written in index notation as dxl, del del xl, and then L gets summed over, so it reproduces all three when you perform the sum. So this quantity looks like a dot product of two indexed objects, dxl and del del xl. Some people write it as del L in an abbreviated notation. We will do that as well. dxl, the differential amount change, lth component of that in the position vector. So differential change in position vector lth component times this del del ddxl quantity, partial derivative with respect to lth coordinate. So these two, because this index is rotated, this looks like a dot product, ALBL. Instead, in place of L you have dx, and in place of B you have this derivative operator. So this is what we will call the gradient operator. Okay. So the gradient operator has the lth coordinate to be del del xl. So gradient operator, the kth component, so this is the basis element, is equal to del del. So del k means del del xk. So I've written a short notation which is much nicer. Instead of writing this del del xl, I've just written to be del k. Okay. So ek hat del k. So we have a basis expansion. There's a basis element and then there's a component. But mind you that the basis element, usually we are accustomed to writing it on the right. However, because this is a differential operator, anything on the right will get differentiated, and we don't want the basis to get differentiated. So that's why we've written the basis on the left. Okay. So one thing about this ordering is very crucial. In fact, that's why many people get problems wrong. Whenever they write this is fine. You cannot write the other way, which is del dot dx. That is wrong, because del will act on dx, which it doesn't. And the del is only acting, derivative is only acting on phi. So you should always observe this. You should write the object on which the del is acting to the right of del, okay, or right of the gradient operator. In this case, the derivative is acting on phi, so I've written phi to the right of the gradient operator. Okay, but this must be observed. Many people write this, make mistakes in the exam when they write the phi sandwich between the dx and phi del, or to the left of the del, or somewhere here. So that all those expressions will give you wrong answers, and you lose credit. Okay, now next two quantities on the list are also differential operators, which are known as divergence and curl. And the difference is that here the gradient was acting on a scalar quantity. Now we look at derivatives of a vector quantity. There are two ways of defining, because the gradient operator itself acts like a vector. There's two ways we can make it act on A. One is the scalar way, when we take a dot of this. If we take a dot of this, we know this should be the indexed way of writing is kth component, but kth component of the gradient is the partial derivative with respect to the kth coordinate del k. So this is same as del k xk at location x, of course. So this is a scalar quantity because everything gets summed over, and you can check that indeed it transforms. If you put prime, then write down the transformation rule of a to be o, a, k, whatever, then indeed that transforms like a scalar. So unprimed will reduce to unprimed. We call this to be the divergence, and this is the expanded way of writing this whole thing. If you sum over all k equal to 1 gives you this, k equal to 2, and k equal to 3 gives you this. Okay, so this is a scalar quantity. So gradient of a scalar gives you a vector, and divergence of a vector gives you a scalar. So you should remember these. It's better to commit to memory how to take the gradient and derivative, because you'll need them so often. It's better to commit. It's more efficient if you commit them to your memory. And then, of course, we have a vector and a vector operator acting on a vector field. And instead of dot product, you can also take the cross product, right? That is called the curl. Curl of a vector field is given by this quantity. So curl, because it's a vector, it will have components along some bases. And the component, kth component, as you know, is given by this some formula. Let me just go back for a second. Yeah, so this is the formula for cross. Instead of A, imagine to be the gradient operator. Instead of B, imagine the big A. And then that should be the kth component of that should be epsilon ij k del I aj. Del I aj, right? This is known to be the curl or the circulation density. Now the nomenclature, there is a reason why you have such terms, divergence and curl. And you might ask, what is diverging here and why is it, what is rotating or curling around? What is the circulation you're talking about? So this will become clear when we look at the geometrical interpretation of divergence and curl, hopefully in the next lecture, and this will become very abundantly clear. One way of getting accustomed to these vector derivative operations is to learn some identities. So you can do this exercise yourself. I'll put up some notes in which I've done these, but you can also look them up in Griffiths or any other book. The best would be to do it yourself because you already know the rules of the game. You already know the definition. So you already know the rules of the game. Just use your partial derivative knowledge to obtain these identities. First is that if I have a position vector, r is the magnitude of the position vector. So nth power, n is some integer. Nth power of that is something which we will use very often in electrodynamics. Position vector raised to the nth power. For example, we have inverse square force, in which r is r to the minus 2. You will have n equal to minus 2, right? So you'll have situations arising frequently in electrodynamics where you have to take a gradient of position vector, magnitude of the position vector raised to some power n. And you can show that this is equal to, following the rules written in the previous two slides, is equal to nr to the n minus 2 times the position vector itself. And then, of course, we can look at the divergence of the position vector, because I said divergence is defined only for a vector field. We can use this formula and replace the a by the little x, which is the position vector. So del x1, del x1, del x2, del x2, del x3, del x3. All these are 1, so sum of 3 ones equal to 3. So again, something I would say that it's something which you should know so well that it becomes a part of your memory. Divergence of position vector is always 3. Okay. But about the curl of the position vector, curl is defined, the kth component of the curl is defined epsilon ijk del I xj. So del I, remember this is the derivative, with partial derivative with respect to the ith coordinate. The partial derivative of the jth coordinate with respect to the ith coordinate is delta ij. This is a rule familiar from the rules of partial differentiation, right? Because when I is equal to j, it is equal to 1. When I is not equal to j, equal to 0. That is exactly what Kronecker delta is. So del I xj is delta ij. But then this quantity is equal to 0. Why? The reason is because in Kronecker delta ij is symmetric in I and j, and epsilon ijk is antisymmetric in I and j. Whenever you have such a combination in which you have a contraction, because these indices are indeed dummy, when you have contraction of a pair of indices which is antisymmetric in one and symmetric in the other, this should become minus of itself. And you can show this by relabeling I to be j and j to be I, and then swapping I and j. This guy will be symmetric under the swap, so it will not pick up a sign. This will pick up a sign, so it will be minus of itself. So any quantity which is minus of itself is 0. Okay, so these two are very important identities which you need to know, and this one as well, that divergence of position vector is 3 and curl of position vector is 0. and gradient of r to the n, r is the position vector magnitude, is given by this formula. Now we can introduce a second order derivative which is known as Laplacian, in which we take the dot product with the gradient operator with itself, right? And it's written usually as del square. This is in boldface, so when you're writing in the exam paper, you should put a vector and then square it, okay? So it is divergent dot gradient dot gradient. We can write it in coordinate form as this sum over second order derivatives, partial derivatives. You can check for yourself. In coordinate notation, this will be del L, and then when you expand, when you write down the sum explicitly over all L, it gives you this. So an important identity associated with the Laplacian is this. In addition to taking gradient of the scalar quantity, we would be interested in taking Laplacian as well. Mind you, the Laplacian is a scalar quantity, so the result will be a scalar. So this is equal to n times n plus 1 r to the n minus 2. Of course, this result doesn't hold when n is equal to minus 1. Right? And this is obviously true because 1 over r. Now 1 over r, we know it changes, it falls off as we go away from the origin. So the second order derivative cannot be 0, but the right hand side tells you that the second order derivative is 0. So there is kind of a contradiction here. So this formula only holds when n equal to minus 1, and we will see that n equal to minus 1 case is a bit special case. This formula continues to hold for all n, but the Laplacian formula doesn't hold for all n. For n equal to minus 1 is a special case, and it will require us to invent a new quantity to put on the right hand side, which is known as the Dirac delta, not the Kronecker delta, but the Dirac delta function. Okay, so I think we are done with differentiation. Now we need to learn about two prominent theorems, which are basically the generalization of the fundamental theorem of calculus, the very first thing you learn in differential calculus, in integral calculus of definite integrals. And we need to do this analogous thing here for multivariable. And these theorems are known as the Gauss divergence theorem and the Stokes Curl theorem, because one involves the divergence and the other involves the curl, which are the two kinds of derivative operators defined for a vector quantity. For scalars, we don't have as many, and because for the scalar we can only define gradient, and for tensors also we don't have such theorems. This is just for vectors. As I said, these should be thought of as vector generalizations of the fundamental theorem of vector calculus and single variable calculus. So what is the fundamental theorem? We have derivative of some function x integrated over some range. So in the range a and b, between a and b, in this interval, it is being integrated, and it takes the value. The answer is that the value of the function at the endpoints, right, at the boundary of this. So derivative of some function is equal to the values of the function, or minus. If you think of it, this is actually minus because of the outer normal. You can think of it in this way. So this depends only on the value at the endpoints, or the boundary of the segment. So let's look at, with this knowledge, let's look at the Gauss divergence theorem. What do we have here? So left hand side we have some volume V, and then the volume integral of a scalar quantity, which is the divergence of a vector field. Divergence of a vector field is a scalar quantity which is being evaluated, which is being integrated over some volume V. And Gauss theorem says that, well, this integral over the volume V is equivalent to doing a surface integral of the flux of A over the boundary of the volume V. So let's look at the diagram. We have some volume V, and this is the volume element, this little cube, and this volume V, we're doing the integration over volume V, and then this is equal over the surface which is enclosing the volume from all sides. The flux n dot A gives you the outward, because n hat is the outward normal, there's this tiny area element ds, and n hat is the outward normal. So n dot A gives you the outward flux of A. So it says that the surface integral of the outward flux is equal to the volume integral. So this is exactly like the fundamental theorem, because these are the values at the boundaries of the integration domain. So here we have the integration domain V, and S is the boundary of that. So this should be thought of in the same vein as the fundamental theorem of single variable calculus. There's a second theorem, which is Stokes theorem, in which we consider not a volume integral anymore, but a surface integral. So this gray thing is this two-dimensional surface. You should think of it, because the inside volume is not included. We are just looking at a surface, and this surface is open, right? It has a boundary which is given by this line dl. So three-dimensional volume has a boundary which is a closed surface, two-dimensional surface. Here we have an open two-dimensional surface, and its boundary is a closed to one-dimensional curve, closed line. So what we have, Stokes theorem tells you that the curl of A, when you measure the flux of curl of A on this surface, so this is a small surface element and then the unit vector. So curl of A dotted with n, so that's the flux of curl of A over the surface, is equal to the line integral of A. Line integral of a vector usually means dot product with the tangent vector, or not line element, which is line element dl, which is this little vector pointing along the tangent and of length dl. Line integral of this vector field on this closed curve, which forms the boundary of this surface. So one example would be, consider this volume to be the sphere, then V is the sphere and S is the two-dimensional V to be the ball, three-dimensional ball, which is the radius r, and then S would be the sphere, two-dimensional sphere, which forms the boundary of the ball. In this case, for Stokes theorem, you should think of an hemisphere. Think of the hemisphere, and then this dl is the equatorial circle. So again, similar thing. So we have some integral of some quantity, of derivative of some quantity over the domain is equal to value of the thing which is being differentiated on the boundary of this domain, integration domain. Very much in the vein of this fundamental theorem of single variable calculus, right? So these are the pictorial representation. I'm sure this is not very nice, but if you look at books, or even you look at Wikipedia, because these are very standard things, you will see a very nice way of demonstrating pictorial visual representations of how these things work. Okay, so I think this is a good place to stop here. Next class we will pick up where we left off, and I think we need to know a little bit of the geometrical meaning of curl and divergence, so that these theorems become a little more obvious. Right now they're not so obvious, apart from the fact that what I told you is that they are analogs, multivariable analogs of single variable calculus, but we will see why these make sense. This is very simple once you know the geometric interpretation of divergence and curl. Okay, let's stop here. I'll put some supplementary notes in which I will have the derivations for the various identities, which I didn't have time to do in the class. And also I think it is not better to do these things on the class, but instead do it yourself, and things will become a bit clearer. Okay, let's stop here, and we'll catch up next time.